So we're going over a little problem here in class together. Does anybody have any homework questions?
Whoa, that's really homework.
Like,
That's the only thing I need to do. Aiden never shows up, bro. Why did you have to tag Aiden?
we're going to be reviewing today for the quiz. The last quiz is not cumulative. It's similar to your other quizzes in that it just covers the material since the last quiz. There's about 39 questions. About 31 are on the Scantron, and the rest are short answer or longish answers. Your class that I'm in right now is at 9:30, so your quiz will be Wednesday the 18th from 8 to 10 in MAC 219. Online students, you have two different times you can come in. Monday the 16th at 10:30 or 3:30. And all of you, I don't care if you interchange and take the quiz at one of these other times, just so you take it, okay? Does anybody have any questions before we review?
So like if we wanted to, we could do it like 10:30 to 12:30. That one.
Yes.
Oh, okay.
Yeah.
Like actually?
Yeah, so if you wanted to take it at a different time, you can. Just make sure you get in the correct classroom. So that, yeah. These two will be a little crowded, right? Because you see there's, like, you can't all come to that. You can't all come to one of these, or else there won't be enough places to sit, and I'll have to say, no, you're going to have to sit in the hall or something. We'll figure it out. Anybody have any questions? Then we'll be reviewing, so I'll split you up into groups. We have about 10 sections to go over. This is the review from Canvas, the Canvas homepage. Go ahead and print it if you haven't, or take a look and get it online. So I need groups of about 2 today because we have about 10 sections. Do you mind turning around and working together? Would that be okay? And then how about you two work together and you
Jasmine's
two?
coming. She's still going.
Okay, so you and Jasmine can work together and you two. And then, are you a group of 3 or 4?
She has a printout, so we can be.
Then I'll give you 2 sections. So if you want to do that, and then you two can work together. So I'll give you 4.7, please. Okay. And you can do 7.1 with Jasmine. Then can you two please do 7.2?
7.2, gotcha.
And your group gets 7.2 and
7.2 is easy.
7.4.
Oh, yeah.
Your group gets 8.2. I don't think I gave your group one, did I? No. You can have about 9.1. And your group gets 9.2.
This is the triangle.
Oh.
Yep.
That's a carpet.
Should we do 8.3 instead?
No, but we're not doing 8.3.
Oh, okay.
Is 9.1 really simple?
Oh, okay.
It's the one.
Oh, yeah. Okay. Then you have your choice of 10.3 or 10.5. 10.3?
Oh, easy.
So
what for,
There's level 0.
says, become a, like, even after
Just then you got level. And it's at point what?
7.2.
Now you got level 1. Level 1 is
Yeah.
Now level 2.
Yep, or fern or broccoli or fern.
Level 2 is bam, bam,
Raise your hand if you're stuck.
bam, bam,
There we go.
bam,
You only need to do 30.
Yeah, that's what I'm saying. That's 3 for that
You
variation.
didn't do the last line.
Oh. Now the
triangle is
triangle, yeah. Oh, so I have to do level 3. These days just so you can do more work. Level 12 level 3 is complicated. I'll back down to the challenge. Alright. So it's gonna take a while. No, I'll do the trains. I like drawing.
Are you an art major?
Yeah, one of you.
Please look up the Mindscapes on Wiley Plus, the read study practice.
Here we go. This is complicated. So.
Can we do the other ones?
Oh yeah, if you get done, go ahead and start your own and go on another section.
No, I have. Oh, so we have to do that.
I know I get out of it. Oh, that's kind of looks weird now. Okay, I got it. There we go. Boom, I'm a pro. Ooh, level 3. Now level 1 is a triangle.
Triangles is
No, that's level 3. Oh, 2. Oh, no, that's 1. Yeah. Now level 2. Bigger triangle. So there's bigger triangle. Triangles upon its triangles. So triangle. Upon its triangle.
Aw, thank you. I thought it was
And now stage 3 is a huge
Southern girls got a little Milwaukee.
It's huge. It has more triangles upon its triangles. So see, triangle.
Oh, yeah, there.
Triangle.
We got assigned some.
And triangle.
The self-summary. Yeah, I am. Okay. So I'm working on 4.7 just because I've got such a lot. And like, I know how to draw a 4.7, but I'm so bad.
Boom.
Yeah, same.
See, I'm a pro.
Okay, and then that will help. Yeah. But I use different colors. Yeah, that was that. Like, I feel like that makes it.
I need to learn how to draw.
Okay.
So
I know how to draw one. Yeah, it's not good.
yeah, you need to know all that.
I mean,
We got
no,
those.
it's not that hard.
Yeah.
What do we do now? Yeah. Stuff that I am not. Alright, I'm gonna
Draw a cube in zero dimension.
Oh, that's easy. Alright, I got you. Look, now we're gonna dribble scrabble. Boom! Look how beautiful that is. Now, we go 4.7. Alright, kids.
Oh, here.
So 0 dimension. Dimension 0 consists of a dot. Where's the dimension? Now dimension 1 is a line. There you go. Okay, now dimension 3, dimension 2 is a square. An actual cube.
You know how to do a 40 cube?
Are you ready to see the cube?
I know how to do a 40 cube.
Are you ready to see the
Yeah.
We'll still keep it, yeah, we need to make sure we. And we will have a.
I just want to get out of there. My job is, so if I get one day, my last
Is that a good cube?
Not bad.
Yeah, boy.
You know how to do a 41?
Hold up. Can you relax for a moment? We're going too fast.
Okay, that makes sense.
No, I'm not. I'm going very fast for you. Your mind is slow. Alright, now we're doing a 4th dimension. This one is very complicated.
Oh, yeah, the Coke curve.
Alright.
You know how to do a
Are you okay?
Yes, indeed.
Me too.
Are we gonna have to draw this on everything?
Alright, so you make the box. Whoa, that was the best cube I've ever made, bro. Don't you agree?
Did anybody draw?
Bro, that is the best cube I've ever made. That's the best cube I've ever made. Okay. Let's not get ahead of ourselves.
Wait, I don't know. No, how do you? Oh, it's another one.
It's a good thing we get 2 hours for this final. It's going to take me 2 hours to draw this thing.
Okay, let's work together for a while. So 4.7, what did a cube look like in 0 dimensions?
It's a dot.
It's a dot. It's just a point. In 1 dimension? A line. In 2 dimensions?
Square.
Square. In 3 dimensions?
Cube.
So draw 2 squares. Draw 2 squares and connect the vertices. In 4 dimensions, do that again twice, right? Because that's how we get all of our shapes. We take the 2nd dimension, which is a square, and we draw it twice and connect the vertices, and that gives us a 3-dimensional cube. Use a straight edge for your 4th dimensional one. That's the one that's worth the most points. If you want to, use 2 different colors. That helps. So this cube in the 4th dimension is perpendicular to the other 3 dimensions somehow, in a way that we are not able to see in 3 dimensions. Whoopsies. So we're indicating that with our drawing by drawing a three-dimensional cube that's being dragged perpendicular to itself into the fourth dimension. So if you draw your cubes, your 3D cubes as two squares offset from one another and then the vertices connected, that would be most helpful, please. And definitely when it's time to connect the two in the fourth dimension, please use a straight edge. Connect corresponding corners. So back left top to back left top. Back top right to back top right. Corresponding vertices need to be connected. I do check for that. How many vertices am I drawing then when I connect? How many are red ones? I mean, how many red edges, I should say, not vertices. How many red edges? 6. How many corners were there to connect? There's 8 corners. I missed one, didn't I? I missed 2. So there's 8 corners on each cube, and we're connecting them. So that makes 8 edges extra. How many edges does the fourth dimensional cube have? You can count them on your drawing if you've drawn clearly. So look at your three-dimensional cube. How many edges does your 3D cube have?
Is it 12?
Yes, 12. So each of your 3D cubes has 12 edges. And then you connected those with 8 more edges. You connected those 2 cubes together with 8 more edges. 32 edges. You can count the vertices also. How many vertices do you have there? 16. Good, 16. 8 per cube. So Mindscapes 11 and 12, you should be looking at your Mindscapes in the read, study, practice portion of your Wiley Plus. They're not always on your assignments. So go ahead and look in the section under read, and then go to the end of that section. You will find the Mindscapes. So we have Mindscape 11, and 12 is similar. Using the fourth dimension, describe how you would unlink the pictured pair of objects. So we'll go ahead and just draw this pair of links and describe how you'd use the fourth dimension to unlink those.
Is that a quiz question?
Yes. So 11 and 12 are similar quiz questions. How do you use the fourth dimension to unlink three-dimensional objects? Did you get a chance to look at that 4.7 group? Did anybody look at that? Oh, I'm sorry. I would have been asking you. I was like, oh, I'm just dumb.
Yeah, I think it might have been called. Oh, wait.
Does anyone remember how? Yes. Go ahead, lift a portion into the fourth dimension. A portion or piece, probably a piece would be a nicer way to phrase that. Lift a piece into the fourth dimension. Your author has a picture of that. Remember that? So just like in the two-dimensional flatland, if we put a 3D loop down, the two people couldn't see each other, but we could lift the piece up into the third dimension where the two people in 2 dimensions couldn't see it anymore. Well, the idea is to do that in a similar fashion in the fourth dimension. So lift a little piece into the fourth dimension, then you can untangle or unlink in this case. And then when you're done, put the piece back in the fourth dimension. So lift the piece into the fourth dimension. It, quote, disappears from the third dimension. Lift the piece into the fourth dimension. It disappears from the third dimension. Unlink or untangle. Then replace the piece that was in the fourth dimension. So the idea is that the fourth dimension is somehow perpendicular to us in a way that we are unable to see because we can only see 3 perpendicular directions in our 3-dimensional world that we live. So 7.1. What were some natural items that had the sense of self-similarity that a fractal has?
We came up with a couple of ideas. We said a fern, broccoli, and coastline, and then an example of like a man-made one. It didn't ask for it, but a man-made one would be the Sierpinski triangle.
Okay, so in Mindscapes 2 and 3, you were to look at the Sierpinski triangle and the, I can't remember which other shapes, and find a part that's self-similar to the rest. So we'll go ahead and do that with the Sierpinski triangle and the Koch curve. Look at that, your author shows a picture of it. So here's a portion of the Sierpinski triangle that looks like the whole Sierpinski triangle. And so he circled this portion. There's other portions as well. Let's see if I can find. So on the Koch curve, you have this portion of the Koch curve that looks like a smaller, reduced copy of the entire Koch curve. Okay. So you'll need to be able to circle a piece of a fractal that's self-similar to itself. In 7.2, you need to sketch 3 iterations of the Koch curve, and I have that page here, so instead of asking you to show your drawing, I'll just go ahead and put this up. So you have the first stage, then you shrink that down and put it on all 4 line segments to draw the second stage. So these 4 line segments are shrunk and placed on themselves, and that gives you 16 line segments. Then this 4 line segment piece stage 1 is shrunk again and placed on each of these 16 line segments to become 64 line segments. You'll need to be able to draw 3 stages of the Sierpinski triangle. So here's, I should say 4 stages because we start with a stage 0. So you'll need to draw this stage, this stage, this stage, and this stage of the Sierpinski triangle. On both of these, I will give you the first stage so that you remember which is which, okay? Anybody have any questions? Okay, I had a note to make sure we looked at circling self-similar portions, but that actually came up in that Mindscape. Who had 7.3? Okay, so I'll put this up here for the Koch curve. You're going to need to take a fractal like the Koch curve or the Sierpinski triangle or the Sierpinski carpet and find its scaling, its scaling factor, the number of copies needed, and the dimension. Because remember, our fractals fell between the dimensions. They were not dimensions 1, 2, 3, or 4. They were partial dimensions. So the Koch curve, for example, 7.3 group. If I take this portion of the Koch curve, which is the biggest one I can get, so that makes it easiest, how many copies of this do I need to make this whole curve? So we take this little piece and make the whole curve. How many of these shapes do I need to make the whole piece? How many? Let's see. Anybody else in your group? 4. Yeah. We have this one. And we put it here, here, and here. So 4 copies. Okay. So 4 copies. And then the scaling factor. Now we have someone else in your group answer.
3.
Good. The scaling factor is 3. You see how this is 9 centimeters for the whole shape for its length, but this piece is only 3 centimeters. So it's 3 times as big. And you get that from how you made it too. You took out the center 1/3 way up at the top up here and replaced it with 2 copies of itself. So scaling factor is 3, and then you use that formula, either formula that you like. I would put one of these on the quiz, whichever one you like to work with, and use that to find the actual dimension of the curve. Does anybody want to see us going through and finding the dimension?
Yeah.
Okay. So we have the Koch curve, scaling factor 3, number of copies 4. So not everybody has a calculator with ln, so I'm going to use the other one. So we had 3 raised to what power equals 4? What exponent do we raise 3 to get the value 4? What is it?
1.26.
Thank you. So if you didn't know it was 1.26, then try guess and check until you narrow it down. So like it's a number smaller than 1.5 because 3 to the 1.5 is 5, and I need to get down to 4. Okay, so we use guess and check to get to where we need to be. So what did you say it was, 1.26? Okay. And you would need to be able to do similar work with the Sierpinski triangle and with the Sierpinski carpet. I'd like to make sure you know where to find the picture of the Sierpinski carpet. That's in section 1.3. And I'll show you that right there. Okay, so the Sierpinski carpet is sketched. Does anybody want to go over the scaling factor and number of copies for the Sierpinski carpet? Yes? Okay, so the scaling factor, take one of the little squares and compare it to the length of the whole carpet. Remember, the yellow portion is removed on the Sierpinski carpet. So you have this square taken out, and that defines these squares around it. And in each of those squares around it, we repeat the process and take out the center, and that creates squares around it. So I like to work with this middle one. I think it's the nicest, because you can just count off the length, right? The length of the whole is how many little squares? 9, yeah. And so the length of the one little portion that looks like the whole portion, see how this little portion looks like the whole carpet on a reduced scale? So I'm looking at this portion right here. How many squares is that? 3. Yeah, it's 3. Say 1, 2, 3. So this little piece is 3. We're making copies of this piece to make the whole carpet. When we do that, its scaling factor is 3, because we go from a length of 3 to a length of 9. Scaling factor of 3. And how many copies do we need? Did you look in there and see how many copies? 8 copies. Good. See, 1, 2, 3, 4, 5, 6, 7, 8. Because remember, the center is empty. So scaling factor 3, number of copies 8. So you'll go ahead and find what D is using that. Okay. Does anybody want to look at the Sierpinski triangle also? Okay, let's look at the Sierpinski triangle as well.
Do these numbers stay the same?
Yep, they don't change. It's not like you can randomize the Sierpinski triangle. It's what it is, yeah. Just looking for a copy of the Sierpinski triangle. Here we go. Sierpinski triangle. Okay, so pick the largest section that you can to make that's similar to the whole. So this section right here. How many of these do you need to make the whole large size? What is the number of copies needed here? 7.3 group, you know?
What was it?
How many copies of this do you need to make the whole one? 3 copies, that's right.
Oh, the middle's gone.
The middle's gone, that's right. So 3 copies. And then how much bigger is the whole than this part was? What's the scaling factor? 2. Good. So it's twice as long as just that one little piece. Scaling factor 2, number of copies 3. So what were Mindscapes 2 and 3? That was finding the dimension. Okay. Anybody have any questions so far? That brings us to section 7.4, and we'll look at that together on Canvas. So on the Canvas homepage, we have that fractal section toward the bottom with Julia sets. So I'm on the Canvas homepage, fractal generators, Julia sets. So remember we talked about how the Mandelbrot set is created from Julia sets. So if I pick a point that's in the Mandelbrot set, you can look at the associated Julia set. So here's the Julia set that goes with negative 0.13 minus 0.0i. Here's the Julia set that goes with negative 0.79 minus 0.89i. So I'm going to pick some more. Who remembers the difference between Julia sets that go with numbers that are in the Mandelbrot set? So here's a number that's in the Mandelbrot set's Julia set. And here's a Julia set that's not in the Mandelbrot set. So a Julia set, the number negative 0.7 minus 0.5i is not in the Mandelbrot set. And here's the Julia set that goes with it. Anyone remember the difference? What's the difference? 7.4.
It's always going to be connected, and if it's outside, it's not going to be connected.
Good. So the Julia set with numbers that go in the Mandelbrot set are connected. So we can keep seeing connected set, connected set, connected set. So all these numbers, all these Julia sets that go with these numbers that are coming up down here are in the Mandelbrot set. Then you click out here, not in the Mandelbrot set, not in the Mandelbrot set, not in the Mandelbrot set, but very beautiful. Okay. Okay, so now 7.4, you can answer these questions. If you pick a point, a plus bi, that is inside the Mandelbrot set, and use that point to build the a plus bi Julia set, how many pieces will the Julia set have? 1. If you use a point a plus bi to build the a plus bi Julia set, and the Julia set has more than 1 piece, does the point you use lie inside or outside the Mandelbrot set? Outside. And so you'll be asked, you'll be given a picture of a Julia set for a particular a plus bi, a number. And then I'll ask you if the a plus bi lies inside or outside the Mandelbrot set. And you'll be able to tell that because the Julia set will either be 1 piece or more than 1 piece. Also, there's some complex number math that you'll find in Mindscape 6 and 7. So the level of difficulty you can expect is something like about this level of difficulty, to multiply out 2 complex numbers. So here we'll go ahead and practice. Can you at your desk multiply out 5 minus 4i times 5 minus 4i? So you should be using the process called FOIL for first, outers, inners, last. So first is the 5 times 5, that would have been 25. Outers, 5 times negative 4i, so positive times a negative is negative, so negative 20i. Inners, 5 times negative 4i, so another negative 20i. And last, negative 4i times negative 4i. So a negative times a negative is positive. If you're not sure, use your calculator, right? Negative 4 times negative 4. And then you have I times I, so 16i squared. Who remembers what is I squared? Who had this section, 7.4 section? What is I squared? Good, negative 1. So I have a negative 20i, so that's minus 40i. So it's just like adding apples. Negative 20 apples minus negative 20 apples is negative 40 apples, but they're i's. Okay, and then 16 times negative 1, so that's a negative 16. So negative 16 plus 25, that's 9. 9 minus 40 times I. So if that's what you got, pat yourself on the back. Do I see any back patting going on? All right. Any questions? that brings us to 8.2. Who had 8.2? Can you please tell us the definition of probability?
N over T, N is the number of outcomes of G, which is E equals event, and then T equals the total number of equally likely outcomes.
Thank you. Number of outcomes in the event divided by total number of equally likely outcomes. So this is probability definition. You need to be able to use it. You don't have to quote it. Same thing with the law of large numbers. So I'm going to put that on the screen. Law of large numbers. If an experiment is repeated a large number of times, then the relative frequency of a particular outcome will tend to be close to the probability of that particular outcome. So this is a problem to be able to, this is a idea to be able to use. You don't have to quote it. No, you don't have to quote it. To use, not quote. Did you make a chart showing your two dice?
We're just looking at our last one that we did.
Do you care if I put it on the screen? Okay. So there's space on the quiz for you to put a chart like this so that you can just figure out what are the different outcomes possible when throwing two fair dice. And then you can use your chart to answer questions. These again, this is to use yourself. There's not points for this chart, but I think it's very useful so you can readily see what outcomes are possible. These are all problems that show types of probability you might have to do on a quiz. Mostly things like dice. I should say always things like dice or coin tosses or jelly beans, that kind of problem. Does anybody want to go through an example of that? Okay. So let's look at the dice table that your author gives us, and let's find the probability of rolling a total of 6 or 4. Let's find the total of rolling a 6 or a 4. Okay, so this is the chart that you're going to make. Only you don't have to draw the pips. You can just put the number. So we're looking at all the totals that come out to a 6 and all the totals that come out to a 4. So we had 1, 2, 3, 4, 5 ways to roll a 6. And then a 4, 1, 2, 3. So that makes... Now I completely forgot. What was the one for 6? 1, 2, 3, 4, 5. 1, 2, 3. So 8. 8 altogether. 8 out of 36 possibilities. You can leave the 8 out of 36. If you want, you can reduce it or write a decimal. Anybody have any questions? So you don't need to know 8.3. 9.1 was a reading section, just like you would read in any of your classes. It's different scenarios of poorly collected data or poorly displayed data, and you should be familiar with those scenarios in order to answer questions. So hopefully you printed it out already and you underline different areas to remind yourself of what's going on, and then you can just review that.
We don't need 8.3?
We don't need 8.3. Nope. 9.1 also has some mindscapes that you should look at. You should be able to answer those after reading 9.1. For example, look at number 4. Suppose .com entrepreneurs want to know what percentage of people use the internet. They sent a questionnaire to all email addresses asking whether the recipient uses the web. What percentage of the respondents is likely to say that they use the web? Yeah, I can see you saying 100 because otherwise they would not have gotten your questionnaire. Okay, so that's an example of poorly collected data. So I would suggest you read through all of those mindscapes that are in the back of that section. That brings us to 9.2. Who has 9.2?
We do.
You do, okay. What is the mean? How do you calculate it?
Because all the numbers added up and divided by the amount of numbers there are.
Good. Add up all the data and divide by the number of data points. So don't get that mixed up with the median. Now what is the median?
The middle number and it's between two, you add divide by the
So once you order the data, then the median is the middle number. If there's two middle numbers, divide them, average them.
So do we need to know like the interest on the process? I think that was random.
We'll get to the interest one, yeah. Can I show your box of whisker graph and your histogram, please? So here's your histogram. Histogram always lists the frequency of a particular score. On both the histogram and the box and whisker, you'll see that we have these beautiful, consistent scales, no breaks in them, no changing the scale from 50s to 25s. They're always consistent. You have title on the top and the bottom. The frequency also has frequency on the vertical axis. You do not have a vertical axis on the box and whisker graph. Box and whisker graph then has the median and the first quartile and third quartile to create the box, then the maximum and the minimum for the whiskers. So you will need to be able to do 5 number summaries.
Thank you.
What were those mindscapes? Did you get a chance to check them?
No.
I think they're finding 5 number summaries, means, and medians, so make sure you're able to do that. So is this the formula you're asking about? This is going to be printed on the quiz.
Can you go back to your note real quick?
Sure.
Oh, second. Thank you.
Yep. So we looked at a number of problems where you'll need to be able to calculate the interest. We did that in class, and that's what these are examples of, and that's what you'll need to be able to do on the quiz. And then in 10.5, we looked at preference diagrams. Remember, they're labeled backwards because what you make when you're making a preference diagram is where you would prefer to get what section you would prefer to have if the point that we divide with is placed in one of these areas. So for example, if we're going to put a point here, it's going to fall in one of those areas. It looks like this point would fall in the preference diagram for west. So we're saying we want the west section if the point falls in the west area. We're wanting the section that's labeled up here. That's why they're labeled opposite, because then you get a really big section for west if the point falls up here. Whereas if the point falls on the border, then we're saying I'd be happy with this east section, or I'd be happy with the west section, the letter labeled. I'd be happy with either one. So we have some examples of this, 3 different preference diagrams overlaid, put on Canvas, and we went over those in class, and that's what you'll see for your quiz. Does anybody want to go over one of those? Is that a no? That was a no face? Okay. All right. So we did those in class on Wednesday, and you can certainly look at the video to see how those are done if you don't remember. If you have any questions, see myself or see the tutor. I'll see you next week. Have a good weekend.
I'm going to see if I can find that.
I better shut the video off in case it's